Good morning to all. I am Dr. M.SHANTHI, Professor of Chemistry at Annamalai University. Today I am going to discuss about photo-electron spectroscopy. This photo-electron spectroscopy is one of the analytical technique. So here different types of learning objectives are discussed. First one, introduction, then principle, then types, then analysis of valence and core electron binding energy, photo-electron spectrum, then measurement technique, application and its limitations. First we see the introduction about photo-electron spectroscopy. The PES spectroscopy is an analytical technique used to determine the relative energy of electrons in atoms and molecules. This technique is applicable to samples in gaseous, liquid and solid states. The depth to which the atomic and molecular levels can be investigated depends on the upper limit of photo energy used. The basic principle of this technique: here the collision of photons with atoms or molecules results in the ejection of photoelectrons, that is, it is simply called as a single photon in and electron out process. The kinetic energy of the ejected electrons are further analyzed by analyzer. Here this principle is given the form of picture. Here M indicate the sample atom or molecules. Here H nu is photo energy. Then bombardment of this H nu with M, we can get the cation and ejected electron. Then the kinetic energy of the ejected electrons, that is, it is otherwise called as a photoelectron, which are monitored and studied, and we can get the nature of the compounds. The kinetic energy of the ejected electron is recorded by spectrophotometer, and it is given by the following equation, that is, E kinetics is related to the following factors: Ek equal to E source minus Eb minus, that is a work function of the spectrometer. Ek indicate kinetic energy of the ejected electron, E source energy associated with the incident photon, E binding is binding energy of the ejected electron. So it is a work function, I is work function of the inner metallic surface of the PES spectrometer instrument, that is, it is necessary to remove an electron from the surface of the photometer. Then types of photoelectron spectrometer, there are two different types. These types depends upon nature of the source used here. First one, X-ray photoelectron spectroscopy, otherwise it is called as a XPS or ESCA. ESCA meaning electron spectroscopic for chemical analysis, using soft X-ray radiation to examine core electron levels. The energy levels are between 200 to 2000 electron volt. Next one, ultraviolet photoelectron spectroscopy, otherwise it is called as a UPS or generally PS, using vacuum UV radiation to examine valence electron. Here nearly 10 to 45 electron volts are used. XPS is a widely used technique to investigate the chemical composition of surface. PS used for solids, liquids and gases, but has achieved prominence as an analytical technique for solid sample. Next, analysis of valency and core binding energy. First, analysis of valency electrons only by using ultraviolet photoelectron spectroscopy, otherwise simply it is called as a UPS. In the PS experiment, vacuum UV radiation is used as the ionizing radiation with helium resonance lamp with an energy of 21.22 electron volt, indicated as a helium singly ionized radiations. Next category, analysis of both valency and core binding energy using XPS. XPS is instrumentation incorporates X radiation as an ionizing source, and hence binding energy of both core and valence electrons can be determined. UPS utilizes low energy ultraviolet radiation and is thus limited to measuring binding energy of valence orbital electrons. PS has also been useful in observing vibrational state of molecular ions resulting from the photoionization process. Magnesium and aluminum K alpha X radiations with energy of 1254 and 1487 electrons are employed in XPS. Simple examples for core electrons and valence electrons. This is nitrogen, it is atomic number 7, electronic configuration 1s2, 2s2, 2p3. Here 2s2, 2p3 is called as a valence electron, that is the outermost electron. 1s2 is a core electron which is very close to the nucleus. Next example, oxygen. Here atomic number 8, electronic configuration 1s2, 2s2, 2p4. This is 2s2, 2p4 is a valence electron, 1s2 is a core electrons. The core electron which is very close to the nucleus requires some higher amount of energy. Next, the relative energy of the sample photon and the energy of source are well explained in the following diagram. So, by using helium 1 and helium 2 ion source, valence electrons are monitored. By using X-ray source, there is a magnesium K alpha and aluminum K alpha, both valence and core binding energies are studied. Next, photo-electron spectrum. So, how do you determine the spectrum? By using the binding energy. The spectrum is related to both, there is a binding energy, the relative number of electrons which are incident on the spectrophotometer. X axis we can take the binding energy, y axis relative number. Here a photo-electron spectrum is a plot of number of photoelectrons incident upon a suitable counting device as a function of kinetic energy of the photoelectron. In other words, it is a graph of relative number of electron versus binding energy. It is a simple example for lithium atoms. Lithium atomic number 3, here electronic configuration 1s2, 2s1. 2s1 is a valence electron, 1s2 is a core binding electrons. These core binding electrons which are require somewhat higher amount when we compare to the valence electrons. The binding energy of an electron in an atom depend on its location around the nucleus. Valence electrons have the lowest binding energies. Core electrons have higher binding energies. Each of these peaks correspond to electrons in a different subshell. Another example, that is an inorganic complex example, is the trans trinitro bis ethylene diamine cobalt 3 nitrate. This PS spectrum is given here. Here 3 different peaks are obtained. One is due to the nitrate ion, another one nitrite, another one ethylene diamine nitrogen atoms. In this case, the XPS spectrometer is adjusted so that photoelectron resulting from the ionization of 1s electron of nitrogen atom is given here. There is a trans complex. 3 maxima in photoelectron counting rate are seen, and these are assigned to ionization from 3 different types of nitrogen atoms. Thus, a certain fraction of solid sample loses nitrogen 1s electron from NO3 minus anion. It is otherwise called as a nitrate ion, while other molecules in the sample give NS nitrogen 1s electron from either the nitrate ion, that is a NO2 minus ion, or the ethylene diamine nitrogen atoms. Peak height correspond to the relative concentration of the particular type of atom in a specific environment. The binding energies are expressed as electron volts. 1 electron volts equal to, that is 8067 centimeter inverse, otherwise 23.06 kilocalorie per mole. It must be emphasized that only a single electron is photoionized from any given molecule, and multiple ionization are low probability. Next, measurement technique. Here, how do you measure the PSR? Given here, the main goal in either UPS or XPS is given to the information about the composition, electronic state, chemical state, binding energy, and more of the surface region of solids. The key point in PS is that a lot of qualitative and quantitative information can be learned about the surface region of solids. The focus here will be on how the instrumentation for PS is constructed and what type of system are studied using XPS and UPS. So, it is a figure which shows the component present in the X-ray photoelectron spectrophotometer. Here PS instrument used in XPS, here radiation source or X-ray source. When the sample is irradiated, the released photoelectron pass through the lens system which slows them down before they enter the energy analyzer. The analyzer shown is a spherical analyzer which is a photoelectron pass through the before they are collected at the collector slit. A radiation source, here the radiation sources used are PS are fixed energy radiation sources. XPS sources from X-rays while UPS sources from gas discharge lamp. Here helium lamp or argon lamps are used here. Next, analyzer. PS analyzers are various type of electron energy analyzers. Next one, a high vacuum environment. PS is rather picky when it comes to keeping the surface of the sample clean and keeping the rest of the environment free of interference from things like gas molecules. The high vacuum is almost always an ultraviolet vacuum environment. Next, different types of radiation sources are used here. While many components of instruments used in PS are common to both UPS and XPS, the radiation sources are one area of distinct differentiation. Radiation sources for UPS is a gas discharge lamp, with the typical one being a helium discharge lamp operating at 58.4 nanometer with corresponding to 21.22 electron volt of kinetic energy. XPS has a choice between monochromatic beam of few microns or an unfocused non-monochromatic beam of a couple centimeters. These beams originate from X-ray sources, either magnesium or aluminum K alpha sources, giving out 1254 electron volt and 1487 electron volt of kinetic energy respectively. For a more versatile light source, synchrotron radiation source are also used. It is one of the special type of radiation source. Synchrotron radiation is especially useful in studying valency level, as it provides continuous polarized radiation with high energy of greater than 350 electron volt. Analyzers. There are two main classes of analyzers well suited for PS: kinetic analyzer and deflection or electrostatic analyzers. Specific analyzers. Within the broad picture of two main analyzers, there are variety of specific analyzers in existence that are used in PES. Most common type of analyzer is a hemispherical analyzer, which will be explained in more depth under the spherical deflection analyzer topic. First one, plane mirror analyzer, otherwise it is called as a PMA. PMA is the simplest type of electrical analyzers, are also known as parallel plate mirror analyzers. These analyzers are condensers made from two parallel plates with a distance d across them. Parabolic trajectory of electrons are obtained due to the constant potential difference V between the two plates. So, here in PMA, where the angle between bottom plate and electron entering is 45 degree and the angle between bottom plate and electron exchange is 45 degree. Cylindrical mirror analyzer, otherwise it is called as CMA. CMAs are advantages over PMAs. A CMA consists of two cylinders having potential difference V between them. The entrance and exit slits are well contained on the inner cylinder. In CMA, where the angle between center of the cylinders and electron is 42.3 degrees. R in indicates radius of the inner cylinder and R out is the radius of the outer cylinders. The electron path should be more parabolic than the overlay elliptical shape shown here. Next one, cylindrical deflection analysis CDA. CDS consists of two cylinders spanning at 127 degree angle. It is this reason that CDS are sometimes called 127 degree analysis. The potential difference in a CDA is 2V equal to E0 R in and R out divided ratio of the R in R out, where R0 is E0 is the energy of the incoming electrons in electron volt that are focused. R in equal to radius of the inner cylinder, R out equal to radius of the outer cylinder. These analyzers have high resolution, however, the transmission is low. Next, spherical deflection analysis SDA. SDA are similar to CDA, but they consist of two concentric hemispheres instead. In SDA, the transmission of photoelectron with initial energy E0 occurs along a path where R0 equal to ratio between R in and R out whole divided by 2. Since SDA is the most common prevalent type of PS analyzer, they will be discussed in more depth than any of the previous analyzers, as a thorough understanding of how they apply to PS is theoretically of greater importance. Its a figure shows there is a common SDA analysis. Here only photoelectrons of correct energy are able to pass through the detector with right arc and exit instead of colliding with side walls of hemisphere and becoming lost. General applications of PS spectrometer. UPS used to study electronic structure of solids. It is used to study adsorbed molecule on metals. Determination and assignment of bonding, non-bonding and unbonding molecular orbitals. The binding and orientation of adsorbed species on surface of the solids are studied. XPS is routinely used to analyze inorganic compounds, metal, alloys, semiconductors, polymers, catalysts and biomaterials. There are several areas suited for measurement by XPS. First one, elemental composition. Number 2, empirical formula determination. Number 3, electronic spectra. Number 4, binding energy, layer thickness in the upper portion of surface. So, specific example of systems studied by XPS are: number 1, analysis of stains and residue on surfaces. Number 2, solid salt reaction. 3, study of composition of thin films. 4, the distribution of elements in surface structures are determined. General limitation: conventional UPS has relatively poor resolution. Samples for XPS must be compatible with the ultra high vacuum environment. There is a pure samples are required here. XPS spectra also take a long time to obtain. Thank you.